Okay. I want to talk about the dot product, the Euclidean inner product. It's sometimes also called the scalar product. And the reason it's called a scalar product is because we're going to multiply two vectors and we're not going to get a vector. We're going to get a scalar. So if I'm in two dimensions, and I have two component form vectors, u and v, then they're, if I'm in two dimensions, sorry, can't give you 1 and 2 and 1 and 3. That's not going to help. They both have to be in the same space. Then their dot product comes from multiplying corresponding entries and then adding. So I take the first two numbers in the first number in each of the two vectors, multiply them together. The second number in each of the two vectors. But the result is that this is a number, not a vector. This works for any length of vector. As long as the two vectors are the same length, I multiply and add. What's that dot product? Zero. 2 times 3 is 6. 1 times 0 is 0. 3 times -2 is -6. The result here is 0. Now I can actually prove this, but to do so requires me to use something from a more advanced analysis course called the Cauchy-Schwarz inequality, that this turns out to relate to a lot of other things. It's not only true in 2 and 3 dimensions, it's true in any dimension. You will often also see this written in matrix terms, because this is the same sort of matrix idea you get when you multiply across a row and down a column in matrix multiplication. We're just treating them both as vectors. If I turned this to be vertical, we'd go across the row and down the column exactly the way you do in linear algebra. And if you've not done matrices yet, ignore that. Some nice properties. You take the dot product of a vector with itself, you get the square of the length. Since all of this multiplication that we're doing here is just multiplying real numbers, it doesn't matter what order you multiply real numbers in. So if I have vector A dot vector B, I get the same result as if I do vector B dot vector A. The distributive rules work. A dot B plus C is the same as A dot B plus A dot C, which is good because I'd like the rules that we are used to still hold. Scalar multiplication can be distributed as well. Let C be a scalar, then C times A dot B is the same as CA dot B is also the same as A dot CB. I put that C wherever I want. It can be on the first vector, the second vector, or done after one. And if one of the two vectors is zero, what's the component version of zero again? Zero through the whole thing. So zero dot any vector at all is zero. And this is why I use the little harpoon, because on the left side, that's the zero vector. On the right side, that's the scalar zero. But that just means that this new operation on vectors obeys the rules we like. And that's helpful, because that means I don't have to try and invent a bunch of new ways to try and figure out what's going on here. Questions? You've seen this before? Physics class, trig, maybe. We've done this in a lot of places. Yes, sir.
The A vector times A vector. Why do you the distance then?
So let's actually write out what happens when I take a vector, A1, A2, A3, and do the dot product A dot A, right? I'm going to take the first number in A and multiply by the first number in A. That's A1 times A1. And then I'm going to get A2 times A2. And then I'm going to get A3 times A3. Isn't that our distance without the square root? There you go. As a matter of fact, in some textbooks, we use the dot product to define length rather than using Pythagoras to define length. And so we say, oh, the way we're going to define the length of a vector is to take the dot product with itself. Now that requires me to have done the dot product first. But that actually is a more general way of defining length. And us abstract mathematicians, we like to generalize things as much as possible. Better? All right. Okay. Let me draw a picture. I've got two vectors, and I'm just going to give them the same initial point just to make my drawing prettier. I'm going to label the angle between these two vectors as theta. Now, this works in 2 dimensions or 3 dimensions. I can draw this picture. It's very difficult to draw a 4-dimensional picture, but there, I've got two vectors that have a common starting point, right? Hold your arms up in different directions. There you go. There's an angle between those. It turns out that with a little bit of trig, I can think about the triangle I've got here. That's the vector A minus B. Sorry, no, that's the vector B minus A. I had to remember which way I drew the arrowhead. I can take the lengths of those, and with a little bit of trigonometry, I can relate the lengths of these vectors to that angle. That's the law of cosines. It's been a long time since trig, right, people? So I don't remember exactly about that, but it turns out on page 808, bottom of the page, they actually go through the entire bit of algebra. I can show that the dot product AB is equal to the length of A times the length of B times the cosine of this angle. Or equivalently, that the cosine of the angle is the dot product divided by the lengths. As long as neither vector is zero, because you can't divide by zero, and zero doesn't have a direction for me to go in anyway, so there wouldn't be a way to do that angle. Hmm. Okay. 2, 2, 1 is forward, left, up. 5, -3, 2 is forward, right, up. So I've got two vectors. What's the angle between them? Find theta for me. In order to find the angle, I need three things. I need the dot product, and I need the length of each vector. Length of A, square root of 4 plus 4 plus 1. Wait a minute. That's easy. Square root of 9. Yay. The length of B, square root of 25 plus 9 plus 4. That's less pretty. 34, 38. Oh, well. Dot product. A dot B is 10 minus 6 plus 2 is 6. So cosine of theta is 6 over 3 root 38, or cancel and write 2 over root 38. And now you can give me an angle. I'm persnickety. I don't care if you use radians or degrees, but if it's specified, please use the specified unit. I knew before you gave me that answer, Ben, that the answer you were going to give me is less than 90 degrees. How did I know that? For the record, this is not the example I have written down. So the answer I got from the example I had written down was 84 degrees. So I made a copy error between my paper and this, but we did the answer here correctly. I'm fine with that. How did I know it's going to be less than 90 degrees? The trig factoid that I'm hoping you remember about the unit circle. Why is that true? Because all of those angles are in the first quadrant. Cosine is positive in the first quadrant. And if my cosine is negative in the second quadrant, and it's at 90 degrees, then my cosine is 0. So if I know that I do this calculation and I got 2 over the square root of 38, I don't know what that number is, I just know it's positive. The answer has to be less than 90 degrees. If I got negative something, then it would have to be bigger than 90 degrees. And if I get 0, then the angle is exactly 90 degrees. Didn't we get 0 in one of our earlier calculations? We did a dot product back here and got 0. So that means that the angle between these two vectors is exactly 90 degrees. That IFF is short for if and only if. Logically, that means that that's like an arrow going both directions. If the vectors are perpendicular, then the dot product is 0. If the dot product is 0, then the vectors are perpendicular. That means if you can define a dot product, you have a way of defining an angle. Remember I said this worked in any dimension you wanted? The dot product worked in 2 dimensions, 3 dimensions, 17 dimensions, 450 dimensions. But if I have things that are perpendicular to each other, they're distant. The closer the angles are, whether they're in the same direction or opposite direction, the closer this cosine is to 1, the more similar those things are. They're either parallel or anti-parallel. Going in exactly the same direction, exactly the opposite direction, 0 or 180 degrees. How do you take a stats course? Any stats. There's this thing called correlation. Correlation tells you how closely related 2 sets of data are, right? The calculation for figuring out the correlation coefficient is a dot product. Correlation is an angle. Your 2 sets of data, either they go together or they don't. And the more different they are, the closer to 0 that angle is. Every statistics calculation I've ever done in Excel spits out this R value, the score, and it's an angle. Son of. Now, I don't know how to see angles in 450 dimensions, but I can use them as a measure of similarity, as a measure of correlation. How connected are 2 things? Questions?
What is the correlation? It's like one best fit of
It tells you about how close the line of best fit is to a perfectly straight line, right? When your correlation coefficient is 1, you have a perfectly straight line data that when one goes up, the other goes up, regardless of what the slope is. When your correlation coefficient is -1, when one goes up, the other one goes down. But that's a perfectly straight line fit. The further away from one you get, the more spread out, the less perfectly in line those 2 pieces of data are, the further away they get from that line of best fit. It's exactly the same calculation. You take the differences between the projected values and the actual values, and then you take the distance and you sum them up. Then you take the distance from the other one and you multiply those together, and lo and behold, that's the dot product. And then you take one and you square it and take the square root. You take the other one, you take square it. That's the length. And it's SSXY over SSX SSY squared. Exactly this. I learned that when I started teaching stats last semester. I've been doing this course for 30 freaking years, and I learned that last semester. My jaw hit the ground. Calc 3 is everywhere. More questions? I gave you the vector 2, 2, 1, and I said it was forward and left and up. That's a really crappy description of which way is this going, right? So how can I lay out a better description of which way something is going? I could use an angle. I could use a couple of angles. So on page 810, we have this picture. Figure 3 here, that shows me a vector sitting out in the first octave, like 2, 2, 1. And then they've labeled 3 different angles here, alpha, beta, and gamma. Now here's the problem. I want to know what these 3 angles are. So alpha goes from my vector to the x-axis. And beta goes from my vector to the y-axis. My vectors up here, those are actually slanted. They're not perfectly horizontal or perfectly vertical. They're at an angle themselves. 2, 2, 1, and the x-axis, right? That curves in 3 dimensions. And gamma goes from my vector to the z-axis, down, from overhead. So I can measure relative to each axis and relative to overhead, declination and ascensions. In astronomy terms, they use words like ascension and declination, and they have these same sorts of meanings. But how am I going to find those? If I'm finding angles, I'm going to use this idea to find angles. I'm going to use these calculations. This calculation right here is the easiest way to find an angle. So let's suppose I have a vector. In the textbook, they call it V. Now, I'm measuring from the positive parts of all of these axes. So when I measure alpha, I'm measuring to the positive side of the x-axis. And since our example vector was in the first octant, that was easy to see. If it's in the second octant, well, then it's a much larger angle. That's going to be more than 90 degrees, right? How am I going to get the cosine of this angle and then eventually get the angle? Well, let me think about cosine of alpha. Cosine of alpha. Cosine of alpha. To use that dot product formula, I need 2 vectors. Well, V is obviously one of them. What's the other vector? What's a vector you 100% for sure know that it points in the positive x direction? We gave that a name, I. Wait a minute. What's the length of I? 1. So this number is 1. But what happens when you do v dot I? Remember, v is in 3 dimensions. And Ben, you said that I was 1, 0, 0. So what happens when you do v dot I? What do you get? And that's it. Because v2 gets multiplied by 0 and v3 gets multiplied by 0. So this is just v1 over the length of v. Wait a minute. I've seen that before. Where did I see that before? Yesterday. I think it was over there somewhere on the board. The unit vector, right? We took a vector and we divided by its length. What happens when I go to do cosine beta? Cosine of beta is going to require me to use the y-axis. What am I going to use instead of I? What was that mumble yell? I'll use j. And when I go to the z-axis, the vector that points that way. Okay. So I can do all of these calculations but since the length of j is 1 and the length of k is 1, and I know how to do the dot products with my components, these turn out to be exactly the numbers we get when we found our unit vector. So when I have v is the vector 2, 2, 1, we already worked out the length of that vector. What was the length of that vector? Square root of 4 and 4 and 1. Okay, length of v is 3. The unit vector in the same direction is 2/3, 2/3, 1/3. But those are the cosines of the angles. Question, grab your calculator. What's the inverse cosine of 2/3? Say again? 48.2 degrees. There you go. And cosine inverse of 1/3 is going to be steeper.
70.5.
That's gamma. That's the length. Sorry, the cosine, the angle from the z-axis. What was that angle again, Ben?
78.5.
Now, let me think about this for a second. Does this make sense?
70.5.
70. Oh, my apologies. 70.5. So let me think about this. Let me draw the picture in my head here. Remember, I got to stand in the corner and I'm going to say 2, 2, 1. Right? Well, 2, 2 would be at 45 degrees, wouldn't it? But then I go up a little. So the angle has to not just go across, it has to go up. That makes it bigger than 45 degrees. 48. I'm perfectly fine with that. That's from the x-axis. That's also from the y-axis because of the symmetry involved there. And we only went up one, so we come down quite a ways. We're close to the plane, the XY plane. So 70 degrees makes sense. I kind of think I see that. There is a lot of vivid hallucinating going on when I do Calc 3 because I have to try and picture these things in my head. A lot of people really like toothpicks and Play-Doh at this point. You can make the Play-Doh the origin, you put the X, the Y, and the Z, and you put your vector in wherever the hell you want it. Go for it. I had students for a Tinker Toys class. Questions?
I'm not, it's a little bit bigger than 45 degrees.
Okay, so 2, 2, 1, right? So 2, 2, if it was flat, that would be exactly 45 degrees, wouldn't it? Because in the X and Y direction, 1, 2, 1, 2, this is 45 degrees, right? But now I've got to come up. In the way I've drawn this picture, X and Y are flat, so Z is pointed out at it, yes? So when I come off the screen, isn't it going to make that angle get a little bit bigger as I come out towards you? It's going to stretch because I'm not measuring on the XY plane, I'm measuring in three-dimensional space. If it's up here like this, I've got to measure up to it. As much as I think I'm a crappy artist, I don't like the picture in the textbook at all. I wish we could grab it and turn it around. So if you look up direction cosine, believe it or not, Wikipedia has a picture you can actually grab and turn. And Math World, the Wolfram Math Dictionary, also has a picture you can turn for the direction cosines. But that's why it got bigger, because I took a flat thing and moved it up, and the distance had to stretch to accommodate that lift. More questions? All right. Another useful piece of the dot product relating angles and vectors is to actually compare two vectors to each other. So again, I'm going to have two vectors. And I deliberately went out of my way to not make either of them horizontal or vertical in the plane, just so we could make this interesting. Something we do in physics a lot is we ask how much of one vector goes the same way as another. So I would ask the question to you, how much of B points in the same direction as A? Now, here's an interesting way to think about this. You've already done this when we thought about taking a vector and getting its components. Only in that case, we asked how much of the vector went in the X direction and how much of the vector went in the Y direction and how much of the vector went in the Z direction, yes? So if I take this picture and I turn it so that A kind of looks like the X axis, I could be asking you how much of B goes along the A direction. We're going to call this vector the projection of B onto A. Sometimes we use the phrase along A rather than onto. I don't care. But we're going to write it in symbols as the projection of B onto A, and the A is a subscript there. That's how I remember it's on A, the projection on A. Oh, we use the word of when we write functions, right? So projection of B on A. All right, wait a minute. How the hell would I find this? Let me go back, turn the picture again. If that was the x-axis, then what do you know about that dotted line there? And that would make a right angle, wouldn't it? That would make a right angle right here. And if that's a right angle, I pull out my trig again. I know the hypotenuse of that right triangle. The hypotenuse of that right triangle is B. So I want to find the horizontal side. What trig function goes with the horizontal side and the hypotenuse? Cosine. And didn't we get cosines from dot products? I'm going to need cosine of theta. So if I want the length of this piece, I'll use cosine of theta. And so the length will be the hypotenuse times cosine of theta. So the length of the projection of B on A is hypotenuse times cosine of theta. But cosine of theta comes from my dot product. What's the formula for the cosine from the dot product? I need a thingy with a dot product inside that sort of parentheses. But wait a minute. There's a length to be on the bottom and there's a length to be on the outside. They're going to cancel. Now, this is the length of that piece of the triangle right there, right? This little bit right here has a length, and that's the number we just came up with. This is sometimes called the scalar projection because it's just a number. It's also given the symbol component. I hate using that symbol. I much prefer length of projection, but that's the same idea. Okay. I'm 99% of the way there. I know how long my vector needs to be. What direction should it go? This number right here is the length of this little bracketed vector. I have a length. I need a direction. How do I get directions without lengths? How do I indicate a direction without a length. We mentioned this yesterday. That just tells me where I ended up. And then it would depend on where I started, right? But if I just want to say go this way, and I'll tell you how far later, how do I say this way without indicating a length? I need a unit vector again. So I can say go this direction, or this direction, or this direction, or that direction by giving you a unit vector whose length is 1, and then I can say go this far. What direction do I want that little piece to go? I want it to go the same way as A, right? So to make the actual projection vector, I take this length and multiply it by a unit vector made from A. The projection itself is this number multiplied by a unit vector made from A. Please notice, this is a number on the bottom. This is a number inside the parentheses. I can put those together and I can write this as A dot B over length of A squared. That's another dot product, isn't it? Number times A. And isn't number times a contraction or an extension of A? Let me go back to the picture for a second. I promise I'll come back and I'll show you this again. I wanted to know how much of B went the same way as A. I took A and I shrunk it down until it was the right length. I took A and I shrunk it down until it was the right length. Son of a... I got it all out of drawing a little triangle. $64,000 question. Why should I give a flying? Who cares? What are we going to use this for? Several different concepts come out of dot products. The one that I use the most is work. In physics terms, work is force times distance. But if my force and my distance are not exactly parallel, then I need to account for that angle. If I wanted to move this podium, I would have to shove, right? I'm taller than this podium. So when I shove on this podium, I'm pushing at an angle. Some of my push doesn't go to the side, it goes down. So I'm actually trying to push this podium partially into the floor. That's not very helpful, is it? So how much of my force is actually going the right way? I have to take the part of it that goes parallel to the direction of motion. So in vector terms, we write force dot distance. I have this cart with all of my crap on it, right? I am pulling at an angle as I walk around with this cart. But the cart itself only moves horizontally. So the angle at which I hold this reduces the force I apply. By how much? By the appropriate cosine of the angle between the direction of my pull and the direction of motion. Page 812. All right, it's not my cart, it's a little red wagon. Here's the little red wagon being pulled at an angle of 35 degrees by a child taller than that. So the handle's not perfectly flat, it's up. And if they pull with a force of 70 newtons and they walk 100 meters, how much work did they do? Okay, I've got a force. The size of that vector is the size of my force. So that vector is 70 units long. I've got a distance. That's 100 meters long. I'd take the dot product. But rather than write this in I and J, I can use the cosine version. Length of the force, length of the distance, times the cosine of the angle, and I come up with a number. 5,734 joules, 5 kilojoules, about a Snickers bar's worth of energy. I don't care what we're doing, whether we're doing it in 2 dimensions or 3 dimensions. I'm moving from point A to point B along a track, but I'm being pushed at an angle to that track. I don't know about you, but I've ridden a roller coaster recently. That hurt. So how much force was done? How much work was done moving it around? See, my wife wanted to go to Universal over the break. So we went to Universal Studios for it. And I rode Hagrid's Motorcycle Adventure, which is a wonderful roller coaster with one problem. One person sits on a motorcycle. Having ridden a motorcycle in the past, but not in the last 30 some odd years, I kept trying to lean. And then the damn thing drops and shoots you for it. I hurt myself. I'm giving up roller coasters again, and I walk around with a limp for the rest of the day. But how much work was done? What's the exerted energy? What's the force? What's the direction? Because sometimes the force and then the track do different things. Okay, I need to make sure you have enough energy, enough work is being done, move you all the way up and over that hill and turn and scare the pants out of everybody who's riding it. This is the way you do that calculation. And it turns out that it's easiest done in vectors. We have a problem when it comes to figuring out how the things curve, though, right? So we'll have to figure out curves as well. I'm not there yet. I'll get to curves. But that's week after next. Questions? I do want to make a correction. I want to get rid of this little X here. Instead of writing force times distance that way, let's put a dot there since we're using a dot product. I don't want to use an X. That means something different. That is what we will talk about on Monday. Questions? I hope you have a wonderful weekend. I will see you all on Monday. Now let's keep our fingers crossed and see if this recording worked properly. Stop.